Team 25009 working on the 3D printer plastic filament verification system sponsored by the Engineering Design Center. The EDC is an on-campus makerspace that allows engineering students access to a variety of tools, with 3D printing being the most popular. However, the EDC generates significant plastic waste due to novice users selecting the incorrect material type, which often leads to failed prints, material waste, cost waste, and machine downtime. Selecting the correct material type is critical since each plastic has a unique temperature and speed setting. Our team was tasked to create a system that identifies common filaments such as PLA, ASA, and PETG using spectroscopy and automatically adjusts the printer settings if a mismatch is detected between the filament loaded into the printer and the filament the user is selected with 75% accuracy. Our system should also stop a print if material loaded violates the EDC material guidelines, which is ASA and PETG. The goal of our project was to create a system that is cost-effective and reproducible so it could be implemented by other makerspaces on campus. I'm Samantha Perry, and I'm studying software engineering, and I'm this team's team lead.
I'm Lauren Froberg. I'm studying engineering management, and I'm this team's procurement lead.
I'm Malcolm West. I'm studying mechanical engineering, and I'm this team's technical lead.
I'm Tage Scott. I'm studying electrical and computer engineering, and I'm this team's electrical lead.
I'm Adrian Perez Gamboa, and I'm studying mechanical engineering.
I'm Shelby Jansen, and I study material science and engineering.
I'm David Sepulveda, and I'm studying electrical and computer engineering.
The goal of this project is to create a system that can reduce plastic waste for academic makerspaces while improving the rate of successful prints. Here, we have a functional block diagram that highlights the four main functions of our system: sensing the material, comparing the materials to our database, verifying the user settings, and finally, logging system statistics. Next, we have our system block diagram, which outlines the four main subsystems: the housing assembly, the sensor assembly, the user interface, and software. This diagram also shows all of the components within our system and their interactions.
Our housing assembly underwent the most design iterations, as maintaining a controlled environment is crucial for our system performance. Some of these optimizations include aligning the sensors to enhance sensor accuracy, having an individual compartment for each of the sensors in order to reduce external interference, integrating slots to facilitate wire connections, and making the filament run through the housing smoothly by adding PTFE tubing, all while keeping our housing as small as possible.
We have three sensors in our system: a spectrometer, a color sensor, and a runout sensor. Our spectrometer collects 18 data points at discrete frequencies ranging from 410 to 940 nanometers. The color sensor returns RGB values that we then normalize to determine the color. And our runout sensor is an optomechanical switch that detects when filament is present, as this is not a standard feature on the Prusa Mini. The color and spectral sensors are the main components in the filament identification process. For easier interaction, we use an LCD screen to display messages on what the system is doing. Finally, we have a manual override button, which lets users bypass our system and start a print anyway.
In order to allow for remote monitoring and management of 3D prints, we incorporated an open source platform called Octoprint. By integrating our filament verification module with Octopi, we enabled real-time communication with the Prusa Minis, allowing the system to take immediate corrective action when it detects an incorrect filament type. To achieve seamless functionality, our team developed a custom Octopi plugin providing flexibility, customization, and optimized control over the printing process. The plugin allows us to perform spectral and color scans for filament verification, adjust printer settings to align with the identified material, detect filament presence, and stop a print if unauthorized material is detected. Here we have a picture of our process flow diagram to highlight the main state changes within our system.
Our final software component is a machine learning algorithm that allows our system to identify the filament that's currently loaded into the machine. Our algorithm leverages principal component analysis, PCA, for dimensionality and variance production, and a support vector machine, SVM, for precise categorization. This roadmap highlights the four main phases of our identification process. The first phase is the input stage, where we feed the 18 characteristic data points from the spectrometer and a qualitative predicted color value into the model. In the next phase, we focus on pre-processing that input data. Pre-processing includes subtracting the dark spectra, performing PCA analysis to determine the principal components, also known as the point of greatest variance, and then splitting apart our data into individual testing, training, and validation databases. The learning phase is where we utilize our support vector machine and the training database to find the best boundaries and hyperplanes for separating the filament classes. Our system uses a radial-based kernel, which allows for non-linear decision boundaries. Finally, once the model is trained, we move on to our prediction and evaluation phases. Here, we utilize unseen data from the test and validation datasets to determine our model's prediction accuracy.
For our design, we used agile methodologies and a rapid prototyping approach, which allowed us to understand critical design elements early, supported early testing efforts, and allowed us to pivot faster. Our modular design allowed us to construct, modify, test, and iterate quickly as the project progressed. By PDR, the team had already ordered key components and began prototyping efforts. By CDR, we had already completed our initial prototype and gained valuable insight into areas for improvement.
From our initial prototype, we saw significant variance in our spectral data, so we decided to conduct a design of experiments to better understand the root cause of this variance and how we can minimize it in our final design. We ran 3 main experiments that explored sensor positioning, sensor heights, and variation in a spool of filament.
In considering how this system could be implemented in a variety of makerspaces, we have a GitHub repository that houses all of our software and our CAD models for people to access. And within our user manual, we will also plan on including instructions to train our algorithm to meet their space needs and desired filament types.
In order to better understand the potential environmental impacts and cost savings of implementing our system, we put together a sustainability business case. In a research study conducted at Georgia Tech University in 2019, they found that 41% of 3D prints fail, with 43% of the failures being due to the printer settings and printer malfunctions, which is the target focus of our project. We recorded the amount of filament extruded from 10 printers at the EDC, and we found that by implementing our system with an accuracy rate of 75%, the EDC could see potential yearly savings of $280, 5.5 spools of filament, and 530 operational hours for a cumulative savings of $10,600, with most of that cost coming from operational hours. Since limited data is available for 3D printing failures in makerspaces, we reached out to other makerspaces to see if they had any data or any anecdotal evidence about why 3D prints fail. Here are some of the responses we received. Our closest comparison would be with Catalyst Studios, since they are another on-campus makerspace, and they said that selecting the incorrect material generated so much plastic waste, they had banned the use of other plastics outside of PLA. By implementing our system, we could potentially allow students to use a variety of plastics again. We hope you enjoyed our video, and we are excited to see you on Design Day. Bear down.